Hey guys, welcome back to question 2 for the 2016 level 2 waves exam. Since it's getting a bit late, I'm going to speed this along a little bit and I'm going to get straight into it. Question 2, water. Tim looked at the pond in the garden and noticed a pattern in the water that caused by the wind. The diagram below shows a simplified pattern of the water waves being refracted as the depth of the water in the pond changes. Refraction occurs at the boundary between the two depths of the pond. The incident waves are on the left of the boundary. Draw an arrow to mark the direction of the incident wave as it reaches point X. Draw an arrow to mark on the diagram the direction of the refracted wave after it leaves point X. So as you can see, the direction is always perpendicular to the always perpendicular to the wavefronts. Okay, so the wavefronts are vertically downward, so therefore the direction is perpendicular. So therefore it is traveling perpendicular. So therefore it must be traveling in the right direction. Yeah, so that's your direction for when the wave fronts are traveling at the incident wave's direction. After it hits the boundary and it refracts, it's going to change direction, and once again it's going to be perpendicular to the wave fronts. Okay, so instead now it's going to be, so as you can see, this makes 90 degrees, so 90 degrees, 90 degrees, 90 degrees, etc. After it refracts, it's the exact same thing. It's going to make 90 degrees with the direction. Okay, so that looks about right. Not really. Yeah, so it should be about there. So this should all be 90 degrees there. And that should be your direction. For the refracted wavefront. This question is that's only an achieved question there. It's real simple right there, achieved. And you need both of them correct. Okay, so which property of a wave does not change when it's refracted? Alright, so what does this mean? Okay, so we know that v equals to f lambda. Okay, so which of these properties waves does not change? We know that the speed changes. If it moves from a different medium, and we also know that the wavelength will also decrease or increase depending on the medium. The only one left here is the frequency. The frequency of the wave will always remain constant. And this is only a one-line answer, so all we have to do here is just state frequency on its own. We don't have to say anything else, okay? And the wavelength of the wave gets smaller as it enters medium B. Explains to you what this tells you about the speed of the wave in the medium B. So as you can see, the wavelength gets smaller in the medium B. So if we get our formula v equals to f lambda, lambda has gone down, but frequency has stayed the same. That means a higher number times by a lower number. Well, basically we can just say v is proportional to lambda. So if lambda decreases, velocity must also decrease. So what this tells us about the speed, and so all we have to do is just we just have to mention the formula and what it does. Okay, so in the we don't have to say that. We can just say the speed of the wave decreases with lambda. This is because v equals to f lambda, and f is constant. So therefore v is proportional to lambda. If lambda decreases, v must also decrease. And that's actually all you need to get the grade for this question. So both of these, okay, so you need both of these, frequency correct and II correct, will get you a merit grade. To get an achieved, you have frequency correct here. That's one way to get an achieved, and another way to get an achieved is to say that the speed of the wave will decrease. That's another way to get an achieved. Alright, question C. If the wavelength of the wave in medium A is 0.3 meters and the speed of the wave in medium A is 3.3 meters per second, calculate the wave speed in medium B if the wavelength of the waves in medium B is 0.2 meters. So in this case, we're going to be using a formula, the a formula that the v2 over v1 equals to lambda 1 over lambda 2. Wait, no, that's not right. It's lambda 2 over lambda 1, I'm pretty sure. Yeah, that's right. That sounds right. All right. So we know that the wavelength in medium A is 0.3 meters. So we know lambda 1 equals to 0.3 meters. The speed of the wave in medium A is 3.3 meters per second. V1 we know is 3.3 meters per second. So what is the speed in medium B? So what's V2? If lambda 2 is 0.2 meters, all we have to do is plug our numbers in. Simple. So V2 we don't know, so we just put V2. V2 over V1, which is 0.3. That's 3.3. Over 3.3, and that's equal to 0.2 over 0.3. Therefore, cross multiply again. So 3.3 times 0.2 equals to 0.3 V2. Just need to plug this one into our calculator. So 3.3 times, 3.3 times 0.2 divided by 0.3. That should give you that the V2 is equal to 2.2 meters per second. Alright, so one way to check your answer, this is the most efficient way to check your answer. So as you can see, the wavelength in medium A is 0.3 meters. And the wavelength in medium B, A is 0.3 meters, and B is only 0.2 meters. Because there's a decrease in the wavelength of 0.3 to 0.2, then you must infer that there's also a decrease in the speed of the wave. So your answer must be less than 3.3. So for example, you get your answer as 4 point something. You know instantly that you get the wrong answer, because since the wavelength decreases, your speed of the wave must also decrease, okay? That's a must, okay? So that's the one easy way to check your answer. So as you can see, our V2 worked out to be 2.2 meters per second. That is less than 3.3 meters per second. So therefore, we are on the right track. We can infer that. This question here, that was a merit question, okay? It's a merit question, and merit to get an achieved correct formula and substitution. So getting up to here will get you achieved. Alright, moving along. The pond is large enough that other wave effects can be seen by Tim. At one end of the pond, there are two large rocks that can be made to partially block the waves as they move from left to right. A water lily is floating beyond the rocks. By changing the position of the rocks, Tim can cause the water waves to move the floating water lily. Name the process of which the waves could reach the floating water lily. So when the waves, they're going to travel and they're going to hit an obstacle, what's going to happen is going to be called diffraction. The wave is going to bend, okay, as it hits the obstacle. So all we have to do is we just need to state diffraction here. We don't have to do anything more, just diffraction. Complete both diagrams to show the pattern created by the waves as they pass through the gap between the two rocks in both position A and position B. Alright, so my drawing isn't going to be fantastic, okay, but the two things to remember: if the gap size is if the gap size is smaller or the same as the wavelength, then there's going to be a maximum diffraction, and the diffraction is going to be seen as semicircles. However, if the gap is a lot larger than the wavelength, then it's going to be minimal diffraction, okay? And the second thing you have to remember is that the wavelength remains constant, okay? So when you draw your refracted wavelengths, your refracted waves, the wavelengths must be ensured to be very close, okay? The markers are sometimes quite stingy, okay? So you have to make sure that there's no obvious, like, it has to be pretty precisely accurate, okay? Alright, so drawing your style position B, that's going to be the maximum diffraction, okay? So it's going to be showing as perfect semicircles, okay? So the waves is going to look something like this. Forgive my drawing, it's pretty hard to draw on the iPad, I figured. So it's going to look something like this, and then the wavelength is going to remain constant, okay? So wavelength lambda is going to remain constant, so it should also be... No, that's a bit too small, sorry. it should look something like this. Yeah, it's not the best drawing, I must say. That's pretty bad. And it's just gonna look like it's terrible. Yeah, forgive me for this. It's pretty hard to draw. Alright, so it should look something like this. Okay, it's not a very good drawing, but so yeah, it's not a very good drawing. Okay, but the thing to remember is that the distance between the waves must all be lambda, lambda, and lambda. No change in the wavelength. Okay. For rock position A, okay, there's going to be a minimal diffraction because the wavelength is a lot bigger. Sorry, the wavelength is a lot smaller than the gap size. What am I saying? So what's going to happen is that the waves are going to not diffract as much. Okay, so it's going to be pretty hard to draw. Okay, so it's going to look something like this. Sorry guys, I'm just trying to do the best drawing I can. No, that's too close. That's too far. That's too wiggly. Yeah, it's not a very good drawing. Okay, it doesn't look very good at all. But in terms of the the diffraction, it should look something like this. So there's a minimum diffraction and only the edges are diffracting. So this middle part should actually be straight. I should emphasize that, but the middle should be straight, pretty straight. That's the important thing to remember when drawing the waves. Okay. All right. So I. Oh yeah. Once again, you need to make sure your wavelengths are constant and approximately the same as the incident waves. Okay. Use your answer in part II to decide whether the waves reach the floating water lily using rock position A or rock position B. Give the comprehensive explanation as to why this rock position affected waves more than the other rock position. Okay, so once again, this question, it's asking you about the size of the diffraction. So in rock position B, it was a small gap, very similar to the waves. Therefore, there was a large diffraction, and then the waves created in semicircles, and therefore they're able to diffract really large, and it's able to reach the water lily. However, in rock position A, as you can see, the waves that actually diffract really little because the gap size is a lot larger than the wavelength. Okay, and that means that the waves don't actually refract and why do I keep saying refract? Diffract enough to actually reach the water lily. Okay, so that's what the points you need to mention. Okay. So you need to state. Okay, so it's important to state what you notice. So, the waves reach the lily in B. This is because in B, the gap size is similar to the wavelength, and therefore for maximum diffraction can occur. Maximum diffraction can occur where the diffracted waves waves are in semicircles and is able to diffract and reach the water lily. Alright, so it's able to diffract enough and reach the water lily. And now we're gonna describe number A. However, in A, the gap size is a lot larger than the wavelength, and therefore only minimal diffraction can occur, and only the edges will diffract. This means the waves do not bend enough to reach the water lily. Alright, so that's all you need, okay? You don't have to write any more. So Nia mentioned that the gap size, okay, is similar in B, and therefore maximum diffraction in semicircles, and therefore it's able to reach the water lily. And then you have to link it back to A. The gap size is a lot larger than the wavelength, and therefore only the minimal diffraction can occur, and therefore only the edges are bent, and therefore it's actually not enough to be able to reach the it's not enough diffraction to reach the water lily. And linking everything, so that's part 1, part 2, and part 3, everything is correct, okay? So part 1 is correct, part 2 is correct, part 3 is correct, will get you an excellence. To get a merit, okay, so to get a merit, you need to correct diffraction, and if you have everything correct here, that'll get you a merit. However, to get an achieved, you only need the process or any one of these, so either II or III will get you an achieved. Alright, so thank you for watching question 2 for the level 2 2016 waves, okay? I hope to see you all in the next question, where I'm going to be going over question 3. Alright, see you in the next one. Thank you. Bye.